Okay, so today we're going to go through solving projectile motion problems. So these are just our arcs, like that guy shooting the basketball, and trying to figure out how we would solve for these sorts of problems given certain amounts of information. There's lots of ways we can go about it. If you remember from the last lecture, there's a ton of different variables involved. So let's talk through some of the ways that we can do that. And we have to remember that there are some key ideas of parabolic motion. In the horizontal direction, so along the x, there is no acceleration. Gravity is only pulling down, so that's your y going up and down. But in the x, we have a constant velocity. So we only need to use a constant velocity equation. In the vertical direction, though, we have that acceleration due to gravity, which is 9.8 meters per second squared down towards the Earth. So we can use any of the 5 equations of kinematics to solve for those variables in the vertical direction. So time is one of our most valuable variables because it's going to tell us 2 positions when we have one amount of time. We have our x and our y position. All we have to know is one time amount. And it's also scalar, so we don't even have to worry about whether it's horizontal or vertical. It just has a number to it. It doesn't matter what direction it's in. Time is its own little cool thing. And if we're using the quadratic formula for anything, remember we can't really do negative time. Science says no. Physics says no. Only the positive time. So don't worry about even solving for the negative version of that. Now when we need to solve for the maximum height, remember that at the peak of anything's trajectory, when we're at the very top, if I was to throw this, something that I can break. If I was to throw something up right at the very peak, it actually has a velocity in the y direction of 0 because at some point it stops going up and acceleration to gravity is like, yep, that's my job, and pulls it back down. So knowing that, we can use that to solve for our maximum height because we can always put our velocity in the y equals 0 to try to solve for what's going on there. Also, we know that our parabola is equal on both sides. So if we only know what's happening at ground level, we know what's happening at the start and at the finish of that parabola. So we can divide that whole displacement by 2. And that's going to tell us how far we have gone in the x direction to reach our maximum height. So basically took our parabola, folded it in half, and that's telling us where the peak is going to be at. So some strategies to solve what's going on. A well-labeled diagram. All the labels. And then making 2 columns, one for the horizontal direction, where we really only have 3 variables, and then one for the vertical direction where we have 5. And we want to just fill in what we know and make sure our units match up. So meters, meters per second squared, and seconds. Those are going to be the standard ones that are easiest for us to solve for. And then we want to convert anything that doesn't match, which I had meant to print out a conversion table for you guys before you left. I will get one posted to Classroom. Let me make a note of that real fast. All right, and then we want to make sure we try to keep this organized. So we want to write down all the information, but keep an idea of what we're looking for and what equation we're using. So I preach this all the time as much as I can. Always write down every single variable you have. Write down your starting equation with just the variables. And then if you need to, number your steps because sometimes it can get a little cluttered. So this way it's going to help you keep everything all sorted out. Then we need to set up our coordinate system and then write down which direction is positive, always, and then which direction is negative. Before we put in numbers, you can rearrange your equations. If possible, this is going to be easier because it's going to help you see what cancels out. I like to put in numbers first, but the rearranging them with just the variables can be just as useful. And sometimes it keeps things a little bit simpler. And then keep decimal places for all of your calculated values until you're ready to write your end answer. So it's harder to do on the TI-30 calculators, but if you can go back up and grab a number with, the 12 decimal places it creates, it's just going to give you a much more accurate answer, especially when we're working with those angles and trying to figure out cosine and sine and what's going on to get our exact heights. So I will be very careful when I grade these and check over these to make sure that it's not just a rounding error that has thrown you off. But the more decimal places you can keep in the process, the more accurate your answer is going to be. And then if you're stuck, just try solving for something else to help yourself along. So don't get your mindset on a specific order you have to solve for variables. Sometimes you have to kind of puzzle piece it together and start from another end. And the time is always going to be the best variable to solve for because you can use it for horizontal or vertical calculations. So we have typically about 3 types of projectile motion problems that we're going to see based on launch angle and whether the ground is level. So we're going to go through and look at the 3 different types and do an example together. Excuse me. So our first type of problem is going to be something that's launched at an angle from ground level. So this is like hitting a golf ball off of a tee. It's essentially at ground level, and then it's going to have, it's going to have that parabola shape to it before it hits back at the ground. So at the ground level means that our displacement in the y is 0. It starts at the ground, it goes up in the air, it ends at the ground. So if we just look at where we start and where we end, the y direction is 0. And our maximum height is going to occur halfway through the range, which means that's also half the time it takes for the entire flight path. So we can take that parabola and cut it in half to figure out the maximum height that we're going to get, which means that it's also about halfway through the travel time. And your initial speed is going to be the exact same as your final speed in these cases. So let's look at this problem right here. We have an initial... Oh, sorry, this is just a diagram for these types of problems. So you'll see that we have our component in x stays constant at the beginning and at the end, and also at the middle. Our total displacement from start to finish, we can cut it in half to figure out where this maximum height is going to be. But at that maximum height, we're not moving up anymore. So we're basically paused at the top there for that little brief partial second in time. And then we have our starting velocity. It's going to be the same as our ending velocity. So we have this whole triangle over here where we know typically what theta is and what our starting velocity is. Whatever we solve for our starting velocity in the y is also going to be our ending velocity in the y, because all we're doing is taking that triangle that we start with and we flip it and inverse it to get our final velocity. So our x is going to stay constant the whole way, and all that's going to happen is the magnitude of our final velocity is going to stay the same, so we just change the direction that it's heading. Instead of heading up, we then head down. So this is our kind of split of our horizontal and vertical variables. In the horizontal, all that we really care about is our displacement in the x, so our range, how far it's going, our velocity in the x, and then our elapsed time. In the vertical, we have our displacement in the y, which is from start to finish, and half of that gives us our max height. Then our initial velocity in the y, and our final velocity in the y, which is just going to be our initial velocity in the y direction, but heading the opposite way. So it's our negative initial. Then we also have acceleration, acting only in the y direction, and that's at negative 9.8 meters per second squared, always on Earth. And then our elapsed time, which is going to be the exact same value that we use in our horizontal side. So the first strategy for these types of problems is to solve for time. And to do that, we set our displacement in the y equal to 0. This means that we can cancel out a ton of different things because we've already gotten rid of one whole variable and we already know our acceleration. So then we can find the maximum height after solving for time by dividing that by 2. So that's going to be the half of our parabola. The time it takes us for us to get halfway is the time it takes for us to get to our maximum height. Or you can, I think it's supposed to say, you can find your maximum height by subbing in that your velocity in the y is 0, because that happens at your maximum height as well. So a soccer player kicks a ball on a level playing field. I just realized, am I even recording right now? Am I recording? I don't know if I'm recording. Hold on. Where's my little box? Tell me if I'm actually recording. Sharing my screen. I'm paused. Oh no. Oh no, that says to pause. Okay. So I should be good. Okay. A soccer player kicks a ball on a level playing field with an initial velocity of 11.3 meters per second and an angle of 35 degrees above the horizontal. Find the time of flight, the range, the maximum height, and the final velocity of the soccer ball. So if I'm going to write all these down in either my horizontal or my vertical, I know that my total initial velocity is 11.3. So I need to solve for my Vx and my Vy. So that's going to be my cosine of 35 equals x over 11.3. And then this is going to be my sine of 35 equals y over 11.3. So I can solve automatically for my two initial velocities. That x is going to keep that velocity the entire way through, and then the y is obviously going to max out eventually at 0. But knowing my initial means that I know what my final y velocity is over here, just heading in the other direction. So we want to find the time that the flight takes, the range, the maximum height, and the final velocity. So I can already solve for my final velocity because all I need to use is this equation here. So my final velocity is going to be sine of 35 times 1.3. So my final velocity in the y is going to be 6.48, and that's meters per second going down. And then in the x, cosine of 35 times 11.3. So my final velocity in the x is still going to be 9.26 meters per second, and that's going to be heading away. There is no set direction. You could probably just go ahead and say east and it would work out. So knowing that that's the case, my final velocity of the soccer ball in each of the directions is here, and then I can also solve it for my actual final velocity heading in the specific direction. But it's just going to be that guy right there because it's going to be the exact same numbers. So there's my x and y calculations. So they wanted to list out variables in the problem. So I don't know what my x displacement is going to be. I know what my velocity in the x direction is, and then I need to figure out what my time is going to be. In my vertical, I have that my displacement in the y is going to be 0 because I start at the ground. I'm going to end at the ground. And then my initial velocity is at 6.48 meters per second. I don't know what my final is, but I kind of do. And then my acceleration is negative 9.8 meters per second squared, and I don't know what time is. So going back to the kinematic equation, they pulled this one to figure out what my total flight time is going to be. My displacement in the y is 0 because I start at the ground and I end at the ground. I know what my starting velocity is, and then I know what my acceleration is. So I can go ahead and solve for time here. So when I get down to this point, what I did is I set each of these equal to 0. So I have, let me change colors. So I have 0 equals delta t, and then I also can say 0 equals 6.48 minus 4.9 delta t. So I already had one here, and I know that that's going to be true because I'm at ground level when we start. And then I can set it up equal over here as well and solve for my final time, which is the next time that I hit the ground, which is going to be 1.32 seconds later. So then to find the range, because my x is a constant velocity, this is going to be the most handy equation we've got. We don't have to worry about anything speeding up or slowing down. We can just use that our velocity is our displacement divided by time. So I know what my velocity in the x is because I calculated it, and I just calculated what my time is. So I've gone 12.25 meters in the x direction in total in that 1.32 seconds that I have. So now to calculate maximum height, I have two different options. I can say that my final velocity for my y is 0 because at maximum height it would be 0. Or I take that time and divide it in half. Since the parabola is symmetrical, remember I can just fold it in half and figure out what that maximum height's going to be. So if I take the time and divide it in half, I know that that's going to happen at 0.66 seconds, which means I can use that to plug into my equations. So trying to figure out, we're solving for our displacement in the y. I already have my starting velocity in the y direction. I calculated my time. My acceleration is due to gravity. So I can just plug all those in and get my displacement in the y. And remember, that's at half time. So the highest that I've gone in the y is going to be 2.14 meters. It's the peak of my curve. And then I'm just going to head straight back down. So the other way you can do it is to set this final velocity in the y at 0 because it's right before we start coming back down. So it's paused in the air for a brief moment before it heads back down. And you already know your starting velocity from what we calculated. And then we know our acceleration. So we can then solve for y from there. You can do it either way, and it's going to get you the exact same answer. Now to calculate the final velocity, we have now figured out well, okay, so this is kind of, I think, excessive. The total final velocity, we already knew what our starting velocity was because we calculated it out, and we're going to square that plus 2 times our acceleration, which is gravity, and our displacement in the y is 0 for the whole thing because we start at the ground and we end at the ground. So you'll see that we're getting a negative 6.48 meters per second, which is actually what we talked about earlier. When we calculated it back over here, we already knew that our velocity in the y is going to be the exact same as this velocity right here, just in the opposite direction. So you don't really have to do the math again. Although this is a good way to double check your math if you ever wanted to. Okay, so now we have our final velocity in the x, or final velocity in the y. Our x is always remaining the same. So our triangle is remaining the same. And we talked about this earlier, but this is just, they threw this in at the end. But we've already done this. We already had the y, we already had the x. They stay constant from when we started. It's just that our y is now going in the opposite direction. And so since we have the same magnitudes, the magnitude of that final velocity is going to be the exact same. And they gave that to us. They gave us 11.3. And then you could technically solve for theta, but if all three sides are the exact same, your theta is going to be the exact same as well. So we took that starting triangle where they gave us most of the information for it, and that's everything you need at the very end too. No math needed. Yay. So, rounding for the answer. The soccer ball was in the air for 1.3 seconds. It went 12 meters. Its maximum height was 2.1 meters, and the final velocity is 11.3 meters per second at 35 degrees below the horizontal, which again, they gave it to us. We just had to make sure we knew where it went at the end. Okay, next type of problem. So we have a projectile that's launched horizontally from unlevel ground. A horizontal launch means that like you're shooting a gun or a cannon or something like that. So our velocity in the y is going to be 0 because we're not going up or down, we're just going straight across. So we don't even have to worry about splitting that initial velocity into anything because the only velocity that we're going to have is in the x direction. And the maximum height is going to be the launch height because if we're just shooting something straight out, there's nothing that's going to make it go up any higher than that. Just pull it down to the ground. So this is what your diagram is going to look like. Your maximum height is going to be at this start time because all that it's going to do is fall from there. So whatever velocity we shoot out with is our x velocity, and our y is just 0. We still have acceleration due to gravity pulling us down. So you still have acceleration being negative 9.8 meters per second squared. That's always going to be there. But now we have a lot less that we have to worry about angle-wise. So we have our total range for our displacement in the x. But here you'll see all that we can carry forward really is our velocity in the x. We will have a velocity in the y because now we have a different velocity in the y because we started with 0, but we know that it's going to speed up as it falls because of our acceleration. So we actually still need to solve for everything over here on this side. So if I split this up into my two different types of variables, my horizontal and my vertical, this is the same thing that we listed before, and it doesn't hurt to just have this list ready to look at so when you're solving a problem, you know what goes where or what you might need to solve for in each section. So we're going to solve for time using our change in height, and it's going to be negative because we're starting out high and then we're falling down. So we're moving in a negative direction. And that way we can determine the time that it takes for us to hit the ground. And we don't have to calculate anything for our maximum height because our maximum height is just where we started out as, but we need to use the Pythagorean theorem and our tangent to determine our final velocity. So a stunt car is being used in a movie scene. The stunt car will drive off a 74.7 meter high cliff with an initial horizontal speed of 55 kilometers per hour. To film this stunt, the director needs to know how long the car will be in free fall and how far from the base of the cliff the stunt car will land. Could you imagine if you were trying to do this, you had one car to do this with, and you filmed it and you were in the wrong spot to catch the landing? See how important physics is? So we also want to determine the stunt car's final velocity as it hits. So here's our drawing. We know that it's going to be falling 74.7 meters because that's how high our cliff is that we're driving off of. Our initial velocity, they said, was 55 kilometers per hour. Which I'm already noticing a problem. I don't want it in kilometers per hour. So that number is going to have to change into meters per second. So real fast to do that, 55 kilometers per hour, and I want it in meters per second. So I cancel out my kilometers. I have 1,000 meters. And then I cancel out my hour. 1 hour is 3,600 seconds. And then I just multiply those straight across. So I'm moving at 15.28 meters per second. That's going to be the type of number we want to use. Kilometers per hour is not going to jive with anything else we do. So outside of those two numbers, I really don't know anything else. So I've got to figure it out. So where do we go from here? There's the conversion we've got. And then we're going to fill in our variables. So on the horizontal side, I know my horizontal velocity. In the vertical side, I know my displacement because I'm falling 74.7 meters. I know that I'm starting out with a 0 vertical velocity because I'm not moving up or down. I'm just driving straight across. It's like Wile E. Coyote running off the edge of a cliff. Just kind of hangs there until he falls. And then gravity's going to pull me down at negative 9.8 meters per second squared. I don't know my time in any situation. I don't know how far I'm going in the x, and I don't know my final velocity in the y. So I'm going to use my kinematics equations. So we used equation 3 again. It's a classic. It's really great. So in this case, we are starting off with our y. And the reason that we're going to do that is because we know 2 of our variables in the y direction. So it's going to be easiest for us to solve for time. So I have that I'm falling 74.7 meters, and because I'm going down from where I started, it's negative, at a velocity of 0 meters per second in the y direction. But here is my acceleration due to gravity, also negative because it's pulling me down. So I can combine all that and get my answers from the square root of 74.7 divided by 4.9. You're going to get a positive and a negative technically every time you take a square root, but we can't do negative time, ever. Time cannot be negative. So we're going to use the positive root. So it's going to take us 3.9 seconds to fall at 74.7 meters. Now, once we know that 3.9 seconds, I can go over on this side and fill that in, and over on that side. So I've come a really long way already in what I need to know. Now for the range, I'm going to pull that simple equation, or my velocity is my displacement divided by time. And I don't know what my displacement is, so I can rearrange it. My velocity is the calculation that we had to convert to 15.27 meters per second. And then my time I just solved for is 3.9. So it's going to calculate out to give me 59.65 meters. Sorry if I'm running through this real fast. I'm trying to keep this short as much as I can. And then for final velocity, I want to know my final velocity and my y because my x is constant throughout. So if I go back to this guy, I already know that this final velocity of my x is going to be that 15.28. They're using 2.7 repeating. I rounded up to 2.8. So I already know what that's going to be. So I need to solve for my y so that I can get what my resultant vector is going to be. So in the y, I know what my starting velocity is. It's 0. So I can cancel out this whole first set. That goes to 0. And then I have my acceleration and the displacement that I'm falling in the y. So then I can solve for that. And I get, again, a square root, so I can take the positive or negative. But I know that like my velocity is pulling me down, so I'm going to use the negative number. So my final velocity in the y direction is negative 38.26. And then I just use the Pythagorean theorem. So a squared plus b squared equals c squared. Using the x that I already knew, the y that we just solved for, and then I can calculate out that my magnitude for my final resultant vector is 41.2 meters per second. And then I got to find the angle. So I'm just going to use the tangent so my opposite over my adjacent, so my y over my x, to get me 68.2 degrees. So my final velocity is at 41.2 that we just calculated. And then I put the 68.2 degrees there. And then BTH is below the horizon. So technically, this is like ground level. And so we're heading at an angle below that horizon level. So in total, the stunt car's time of flight, it lasts 3.9 seconds. It goes 60 meters. You don't have to write in scientific notation like that. And the final velocity is at 41 meters per second at 68 degrees below the horizontal, or below the horizon. Okay, last type of problem. This is when we have a projectile and it's going at an angle, but the ground isn't level. So when we have this, we have I don't know, maybe we're at the very top of a hill, and when you were kids, remember you would try to punt something down the hill and make your friends go chase it? No, just me? Okay, so pretending that this is level, I might hit something like that. So I have an angle to the horizontal, but it's actually not going to be my total angle because, see, I've got some stuff down there. And then these parabolas aren't even. So I can't take this and fold it in half and get the same thing because my ground level is changing the whole time. So I can't just divide my time in half. I can't just say now that my velocity is the same at the end that it is at the beginning in the y. So basically there's no shortcuts. This is the long haul sort of problem. So here's an example of this setup. Apparently here we're standing on a cliff. Makes it a little easier. So we cannot say, oops, sorry. No, come back. So this guy does not equal our final in the y. But at the very peak, we still have our velocity in the y being 0. That will never change because the gravity is about to take over. And our maximum height is going to be a little bit different because we have to solve for how far the total fall is, not just how far the rise is. And our range is still going to be the whole x. This actually should start right about here and go over. And I have two different angles here. So here I have theta, and here they put alpha. So there's a lot going on. Not super easy. These are the ones that are going to take some time. So I still have the variables in the exact same place that I did before. So I have my horizontal and my vertical variables. They're going to stay the same. And the strategies I'm going to use is I'm going to solve for time using the displacement in the y. So I'm going to use a negative initial height to calculate for my time. And that requires the quadratic formula. We'll go through that in just a second here. So my maximum height is going to happen when my final velocity in the y is 0. And then I just need to use Pythagorean theorem and my tangent to solve for the final velocity. So what we're talking about with the negative initial height is my displacement, I just want to make sure I read it right, from here to here, that displacement in the y is 0. So when I come down here all the way to the bottom, I'm looking at having moved only this much vertically. So however high I start is however far I fall from my displacement. So my displacement in the y isn't 0. I've fallen down farther. So a golfer strikes a golf ball from the top of a 2.3 meter tall hill to the green below. The initial velocity of the golf ball is 20 meters per second and 45 degrees above the horizontal. Determine the golf ball's time of flight, range, maximum height, and final velocity. So if I'm going to draw this out real fast, I have a hill, and it's 2.3 meters tall. The initial velocity of the golf ball is 28 meters per second, 45 degrees above the horizontal. So I hit my golf ball at 28 meters per second. I don't know why I drew an 8. And this angle is 45 degrees. Determine the golf ball's time of flight, the range, and the maximum height and final velocity. So here what I can do is I can go ahead and calculate out what my initial in the x and my initial velocity in the y are going to be. Remember, my x is still going to be the same throughout, so that actually helps me a lot. So this guy is going to come and plop down here somewhere. But I'm going to solve for my x and my velocity in the y. So I have my velocity in x is going to equal my cosine of 45 times 28. And my velocity in the y is going to be my sine of 45 times 28. So in the x, I get 19.8 meters per second. And in the y, I get the same thing because it's at a 45-degree angle. So we're moving equally as fast in the x and in the y direction. So here's a more official drawing of that. So we just calculated the x, and the velocity in x, and it's going to stay the same at all 3 locations. I know the velocity in my y starting out, but that doesn't mean I know anything over on the other half. So now I have to go ahead and solve for lots of little things. So there's calculating out the x and y components, writing out the variables that I have. I know that the ball is going to fall 2.3 meters farther than where we started. I know my initial velocity in both the x and the y direction and my acceleration due to gravity. So again, I'm solving for time, my final velocity in the y direction, and then my displacement in the x. So to solve for the time, because it's going to help me the most, I am going to use equation number 3 from our chart again. So I know my final displacement in the y, I know my starting velocity in the y, and I know my acceleration. But it doesn't solve for a clear time. Instead, what I get is the quadratic equation. So I get to go ahead and use that formula. Negative b plus or minus square root of b squared minus 4ac all over 2a, to whatever tune you learned it to. So I plug all those numbers in. This is another thing, we kind of talked about it, but once you get a graphing calculator, if you get one sometime this year, I will be happy to help you program the quadratic formula in there. So all you have to do is type in what A, B, and C are valued at, and it does the math for you. So if that happens, let me know. So when I'd solve for that, I get 2 times. I get a negative. Can't do negative time. So my time is 4.15 seconds. So it takes 4.15 seconds for the golf ball to strike the ground. So then I can use that time to calculate how far I'm going in how far I'm going in the x direction. So if I go back to this chart and fill this in as I go, it makes it easy for me to see, okay, what do I have left to solve for? The horizontal variables are the easiest to do next. So to give myself a little brain break, I just calculate the range using my velocity equals displacement divided by time, all in the x direction. And then I get 82.17 meters is how far that golf ball traveled in the x. Now to calculate the maximum height, the easiest thing to do is set that second variable, or that second velocity, equal to 0, because that's where it starts getting pulled back down to earth. So when I do that, I plug it into equation 4, I think. Doesn't matter. Nobody else remembers them in that order. But I can plug in all the information that I know. They rearrange the variables first. You can do it either way. And I already know my starting and velocity of my y, my acceleration, and then I can solve for my displacement. So I went 20 meters higher than where I started my golf ball at. Now, because I started on that hill though, so here's my hill, here's where the ball went. If this hill was 2.3 meters, I went, this is not drawn to scale, another 20 meters up. So my maximum height needs to add both of those numbers together. And then calculating the final velocity, now that I know how far, just kidding. I could have technically calculated this already. So I knew what my starting velocity in the y was. And then we know the acceleration is negative 9.8. And the total displacement that I move in the y is just the negative amount of that hill, so how far I fell down that hill. So I can go ahead and plug it in to this equation now. Remember, there's a time where you use it where this guy is going to be 0, and that's when you're solving for the max height. But right now, we're solving for our actual final velocity. And we're going to use the negative number because we know that we're moving down towards the ground to get out of the rain. Boom, 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 boom. And then we can use that number in our triangle to solve for our final velocity vector. So to get that vector, we're just going to use Pythagorean theorem, a squared plus b squared equals c squared. And the magnitude is 28.79 meters. Then I'm going to use my tangent of alpha. You can still use theta if you'd like, that's fine. Just know that the theta isn't the same as our starting theta. Then we're going to do our opposite versus over our adjacent and get that it is 46.5 degrees. So very close to where we started, but not quite the exact same. Below the horizontal or below the horizon. So round it all out. The golf ball's time of flight is 4.2 seconds. Its range is 82 meters, and its max height was 22 meters. The final velocity is 29 meters per second, 47 degrees below the horizontal. It's a lot of math, but it's just using those same 5 equations over and over again. So I'm sure there'll be questions. Please feel free to come to the help session. I'll be there.